Good afternoon. Last week we have discussed about ROS, row operating system. So I guess you might be somewhat familiar with the ROS system. And today we'll discuss about SLAM. So let's get started. So if you think about the core technologies of self-driving vehicles, then it may be easy to understand. So in this figure, this is the self-driving vehicle. So to have some kind of autonomous capability, we have to recognize the environment like this. Like the other vehicles or pedestrians or traffic signs, we have to recognize or perceive the environment. So nowadays, deep learning does this. We gather a lot of data, and by training this data through the neural networks, we can achieve this one. And in case we don't have the map, prior map, then we have to generate the map using the vehicle's onboard sensors like the LiDAR or the vision sensors. And then also we have to localize the vehicle. So you might think that we already have the GPS. So using the GPS we can localize, but GPS actually contains a lot of noises or errors, up to 10 meters in the urban area due to some atmospheric effect and also some multipath effect due to the high-rise buildings like this. So we cannot actually rely on this GPS signal. So in that case, we also have to use the GPS, use the LiDAR or the vision sensor to localize this vehicle. And then we plan the path to the destination that does not collide with the obstacle. And then we follow this path using some control mechanism. So these are the core technologies of self-driving vehicles. But how about nowadays self-driving vehicle functions? Does the Waymo or the Tesla do this kind of thing? Do you think they are properly doing this one? Most of them are done by the companies like Waymo or the Tesla, but web generation should be done in advance. They have some mapping device on top of the vehicle, and they manually drive this vehicle over the urban or suburban area, and then they create some kind of high definition map. So once we have this high definition map, then we can localize the vehicle on top of that HD map and plan the path on that HD map. But without this HD map, we cannot operate this vehicle. This is nowadays situation. So Waymo, that's why the Waymo and Tesla cannot expand their territory to different areas. We specifically have some kind of HD map in San Francisco, LA, Austin, but not to the others. They don't have the HD map in the other areas, so that's why they cannot operate this self-driving vehicle in other areas. This is very big hurdle and also big bottleneck, actually. So we have to have some kind of capability like building the map automatically. Once the vehicle can navigate this area and also build the map at the same time and localize this vehicle at the same time, then it may be very powerful. We can operate this vehicle to any kind of areas without depending on the specific area. So that's the big challenge. And we can do that, actually. So mapping, localization, they are two important parts. And in addition to that, we have to plan the path and also control the vehicle. So they are the three big parts we have to solve, but mapping and localization actually should be done at the same time, because this is like the chicken and egg problem. If we have the map, then we can localize the beacon. If we can localize, then we can create the map quite easily. But if you don't have the prior map, then it is not easy to localize. And also, if you cannot localize accurately, then you cannot create the map accurately. So they are chicken and egg problems. So we can solve these two problems at the same time. So that's called SLAM, simultaneous localization and mapping. We can solve the localizing problem and the mapping problem at the same time. Do you understand? So from real world environment, we first use the sensors to perceive this environment. So we can build a local map using this perception, and also environmental map model can be created using this perception capability. And then we can localize the vehicle based on that. Then we can have the position information, and also the global map will be expanded, will be created. And then we can have some cognition part that plans the path. And then based on this path, we just follow this path by using some motion control capability. Then it will be iterated all the time. So this is the general software architecture of the robots or self-driving vehicles. So localization, where am I? This problem is quite important. Yeah? So this is the big challenge in case we don't have the map. If we have the map, then it can be solved probabilistically. So we will first discuss how to solve this localization problem based on the map, prior map, and then how to build this map automatically at the same time. We will discuss in that sequence. So this shows the overall localization function, how to do this localization based on very primitive information like the encoder information, which can be obtained from the wheels. If the wheel is rotated, then we have some incremental pulses. So based on the number of count of the pulses, we can actually estimate the distance it has traveled for this one wheel. If we have two wheels, then we have two information. Right wheel, left wheel. Based on that, we can calculate the average distance traveled by the right and left wheels, and also calculate the orientation speed by having the difference between them. So this is the encoder information, and based on that, we can predict the position somehow, and this is called the odometry. So odometry, or also the data reckoning. And based on that, we can localize the vehicle based on some external sensors like the vision or the LiDAR, or even the ultrasonic sensors could be used. So based on that sensor information, we can have some matching with the previous map. So if we have the prior map, then we can extract the feature from the map and also extract the feature from the current observation. So if they are matching together, then we can guess that we are in the right position. So if matching occurs, then we can update the position information of this vehicle. So it will be iterated over time. So this process is called the probabilistic map-based localization. So we assume that we have the prior map in this method. Later we will discuss how to build the map also automatically. So odometry, this shows the differential drive robot. Differential drive robot means there are two wheels and there are differences. The velocity differences between these two wheels will be used to drive this one straight or turning to the right, turning to the left. Yeah. If the two velocities are the same, then it will go straight. If the right velocity is greater than the left one, then it will turn left, vice versa. Yeah, so we can control this robot based on these two velocities. So that's why we call it differential drive. The difference of these two velocities will be used to control the steering angle. So if the current location is xy theta, xy is the position and theta is the heading angle of this vehicle, heading angle theta like this. Then in the next step, we have P prime. P prime is P plus delta x, delta y, delta theta. So it will be, the position will be updated like this way. So how can solve this delta x, delta y, delta theta? This is called the odometry. So this odometry information is from these two fields. So we call it the encoder information. So using those field encoders, we can actually calculate delta x, delta y, delta theta. How can we do it? Yeah, it seems somewhat complex, but it just obeys the kinematic law. So you can just derive this one. Delta S cosine theta plus delta theta over 2 is equal to delta x. In here, we have some definition like here. Delta theta is defined like delta S of R minus delta of L over B. So actually these are the differences between the two fields. Yeah. Delta SR, delta SL represent the distance traveled by the right and the left wheels respectively. So those are the traveled distances. So if you divide it by B, then it indicates angular rate multiplied with delta t, time. So that's why we have delta theta for this. And how about delta S? This is the average distance traveled. That means we add them 2 and divide it by 2. Then we have the average distance. So average distance multiplied with cosine term, we have the delta x. Yeah. Average distance, this one, multiplied with the cosine term, we have the delta x term. If we have the sine, then we have the delta y term. So it's quite easy. So we can just add this one to the previous position, then we can get the next position. So we can expand like this way. And also delta S, we can substitute this one like here. And delta theta also can substitute this one here. So this seems quite complex, but this is just the cosine and sine term for x direction and y direction. And delta theta term by calculating the angular rate, angular speed, multiplied with the time delta t. So this is called the kinematic equation for this two-wheel drive robot, differential drive robot. Do you understand this one? And also we can model the error of the field encoder information. So initially it can be modeled by those terms. That is proportional to the traveled distance for the right wheel and the left wheel. Because the more we travel, the more uncertainty we have. Yeah. So we can model like this proportional terms. So this is termed as sigma delta. So this is the original error covariance from the encoder information itself. And given this one, how can we get sigma p prime? Error covariance of the next position. Error covariance of this one. Actually, this one depends on xy theta and also delta s and also delta theta. So we can utilize that to update the uncertainties. So this actually can be derived using the error propagation law. So if you have the original probability distribution like this for x variable, and if you have the nonlinear transform like fx, then we get y. So this is also the probabilistic random variable. So you can see that if you have the distribution like this for x, And if you undergo some nonlinear transformation like this, then we get the uncertainty distribution for y variable like this. So we can propagate the error through this fx. So how to obtain that? So we can just use this error propagation law. Cx is the original error covariance of x variable, and Cy is the covariance of the y variable. The relationship is governed by fx. Fx, this is called the Jacobians. Jacobian matrix defined as some kind of gradient, transpose of the gradient of fx. So if you just multiply this one, then we can get the propagated error from the original x variable. You may already have learned about this one, I guess. In the applied mathematics, you may have learned that. But for the simplicity, you can refer to this Wikipedia, propagation of uncertainty. In here, it says that if you have the linear relationship like f is equal to ax, then the sigma x will be like this. Yeah. So this is the conventional definition of the covariance matrix: x minus mu and each square and expectation of this one will be the original sigma x. And how about sigma f? Sigma f is this function. Yeah. Sigma of this function. This is governed by ax. So you can just submit ax here, ax. Then what happens? So we can get ax minus mu squared and expectation. Then if you rearrange this one, we can get this simple equation. A sigma x, A transpose. Sigma x was the original covariance. Now sigma f is the covariance of the output variable. So we have this relationship. Simply like this one. A sigma x, A transpose. So if you have the linear relationship, then you can just use that. But how about the nonlinear case, nonlinear combination? So if you have this one, and this f is nonlinear, then we can just have the Taylor series expansion around this nominal value, f0 plus jx. J is the Jacobian matrix. If you just apply the Taylor series expansion, then we have this Jacobian term. So if you can see that f0 is constant, it does not contribute the error on f. So we can just neglect this f0 in the propagated error. So you can see that we have f is equal to jx. So we have the linearized relationship. So we can just utilize this one, and we get the same equation. Instead of a, we can use j. So Jacobians are quite useful. So sigma f is j, sigma x, j transpose. So that's why we have this equation. Fx, sigma x, fx transpose. So you can utilize this one in the error propagation. Because this error and those errors are propagated through this nonlinear. This is the nonlinear equation actually. Through this nonlinear equation, the error is propagated and we get sigma p prime. So you can calculate that. Original sigma delta was proportional to the encoder information, and you can see that p prime could be obtained from p plus some terms from deltas. So you have to propagate two terms. P should be propagated and also deltas should be propagated. So we have two Jacobians like here. So you can calculate the Jacobians like here. Gradient of P, you can utilize this one, original equation of P. So you can obtain this one, and also delta RL, delta R, delta R, delta L. Have the Jacobians like this, so you can have 3 by 3 by 2 matrix like this. So once you solve this one and this one, then you can just substitute those Jacobians in front and back, then the error will be propagated. So you can utilize this one. Yeah. So f will gradient of f with respect to x. Yeah. Gradient of f. Yeah, this one with respect to x. Then this becomes 1, 0, 0. Gradient of f with respect to y, 0, 1, 0. Like this. And with respect to theta, we will have to have some derivative of this one with respect to theta. Then we have this, because this is the cosine, this will be converted to minus sine, and sine we have the cosine, and so on. And using that, we can have some probabilistic localization method based on the prior. So we are given the position estimate, prior position estimate, like P, previous P, and each covariance sigma P is also given at time T, and the control input could be obtained from the encoder information. This encoder is just controlled by your own control input. So encoder is directly the control input, and the current set of observations, GK plus 1. So you can utilize the vision sensor or the LiDAR sensor to obtain this current observation. And the map is given. We have those assumptions. And we have to compute the new position estimate, PK plus 1 bar K plus 1. Bar means we are given some observation. Yeah. If this is K, then K's observation is only given. If it is written as K plus 1, then we have K plus 1th observation also. So given the K plus 1th observation, we obtain K plus 1th position. The meaning of this one is like that. So if it is K by K, then we don't have the K plus 1th information. We just have the K's information, and then we estimate or calculate the covariance at time K. The notation is like that. And each covariance should be also propagated and should be obtained. Sigma P, K plus 1 by K plus 1 should be obtained. So we have to calculate those two. How to do that? We have two phases. The first phase, prediction phase. In the prediction phase, the start position is assumed to be null. So we have the initial position x0. As the rover starts moving, the uncertainty grows due to the odometric error. The uncertainty will be growing. So if we have this uncertainty initially, like this at x1 position, and if the robot proceeds using UK, this is the encoder information, and then we have some larger covariances because the error has been propagated. Using the odometry, you can see that using the odometry, the sigma p and sigma delta are always positive. They are always positive, and those Jacobians will be multiplied, and you can see that because this is multiplied in front and back, we can always have some greater value from the previous value. You can always see that this error will be propagated and gets larger in the next step. So the covariance will be getting larger for the original position. So we can get x2 position. This is p, k plus 1 by k. So we are just given the Kaist observation. That means we don't have k plus 1 observation now. And in that case, we just estimate the next position based on the odometric information. So we can have some dispersed covariance for this one. And the next step, perception step. Some exteroceptive sensor like the rangefinder, like the LiDAR sensor or the vision sensor can be used to measure the distance from the wall. There is a wall. We already know this wall in advance because we have the map. And computes the position x2 prime, which is in conflict with the estimated position x2. So because we have this wall and actual measurement is d, gk plus 1 is the k plus 1's actual observation. Actual observation. So we assume that we are in x2. Based on the odometry, we assume that we are in x2. But in reality, we have this observation d. So there is some kind of discrepancy between them. So at here, at x2, we should have this distance, actually, d hat. This is the estimated, predicted measurement, actually. So we predict that we should have this kind of distance, d hat, but in reality, we have d. So these two discrepancies should be minimized. How to minimize this one? So the perception update corrects the new position to x2 prime and its uncertainty shrinks. So we assume that using the prior map, we should be at here x2 and should have d hat. Yeah. But now we have actual observation d at the position x2 prime. So we have some kind of how can I say? The weighted average between them should be applied here. Yeah. Weighted average between them. So it has the larger error compared to this one because we assume that the measurement device is quite accurate. So it will have some small covariance. We have the laser rangefinder, so we have some small covariance. We assume that. So this measurement and this estimation should be weighted averaged, and we get this one. So this is x2 prime. That corresponds to p k plus 1 by k plus 1. So we are given the observation at k plus 1 step, and next step position is estimated, and this will be the beam and covariance. You can see that the covariance will be shrinked. Because we have this information and this information. By aggregating these two information, we always have smaller uncertainty. We'll discuss about that in the later slide. So we now have the updated position right here. So this is the basic concept how the localization works. So we will discuss in more detail about this procedure using the 5 steps. We have some prediction based on previous estimate and odometry, prediction, and the observation with onboard sensors like this, using the vision of the LiDAR and so on. And the measurement prediction based on prediction in the map. So the measurement can be predicted, like in the previous slide, measurement prediction, D hat. And matching of observation in the map. So we can match these two. This is the current observation, actual observation, and this is predicted observation. We know that this is the same one. Those two observations should correspond, should be matched. And then estimation will be updated. So we have some terms like posteriori and priori. If you have this one, pk plus 1 by k, then we call it a priori information. And after some observation, we can incorporate this information, then we can get this value, and this is called A posteriori information. After some measurement incorporation, we call it as the posteriori, but before that, we call it a priori. So those are two terms like that. And graphically, we can also think about this localization method. We improve belief state by moving. Belief means the localization information. So in this is one case, we know the prior map, we know the pillars are located here, but we don't know the exact location of the robot. So this LED distribution shows its probability where the robot is located. So initially, we don't know. So flat probability. Identical probability for all the locations. So at the start, no knowledge at start, thus we have a uniform probability distribution. Second, the robot perceives first pillar. The robot proceeds and observes the first pillar. Then we know that if you observe the pillar, then the robot will be located here or here. Exact location is not possible to obtain, but we can assume that. We have some probability distribution that the robot is located here, they are identical. And if the robot moves further, the action model enables to estimate the new probability distribution based on the previous one and the motion. Action model means the kinematic model or the odometry information. So using the odometry, you can see that this probability distribution will be dispersed using the error propagation. So we have some larger covariances like this for these three locations. And further, if the robot perceives the second pillar, based on all prior knowledge, the probability being at pillar 2 becomes dominant. Because we know that, based on the map information, after observing the first pillar, the probability to observe the second pillar will be largest at this location. How about the other locations? This location is not correct. Because if we proceed like this way, then we should not observe some pillar. But now we observe this pillar. How about this? This one also proceeds like this way and should not observe the pillar. But now we have observed this pillar, so the probability distribution of this location only will be maximized. So this is the localization concept, and this kind of localization is called Markov localization. And calculating all the probabilities for all this space is very time consuming. So we can use some particles to approximate all these positions. So that method is called Monte Carlo localization. So we use set of particles to approximate the location information. So we first disperse the particles around those areas, and the particles will be concentrated on those locations. And as time goes on, only the particles at here will be surviving. So this is the concept. So I'll skip this one because we will not use this one. But this actually approximates this Markov localization. And you should know about this one, Kalman filter-based localization. We will use this one. So if you have the control input, then the system will evolve using the kinematic equation and using some measuring device like the sensors. We can observe the external information, and the Kalman filter actually provides the optimal estimate of the system state. System state means the position information, position and heading angle information of the robot. So we have discussed that we have two information, like having the sigma 1, we have Q1, and Q2 having the sigma 2, covariance like here, then what's the optimal estimate that mixes these two? That is Q hat, and we should calculate Q hat and also the optimal distribution sigma. We are given two measurements, Q1 hat, centered at Q1 and having the covariance sigma 1 square, Q2 hat, centered at Q2 with sigma 2 covariance. And then we should minimize the weighted least square to obtain this Q hat. The most fitting measurement we can obtain. So Q hat minus Q1 squared plus Q hat minus Q2 squared, and their sum should be minimized. So we can find the minimum error by having the gradient information of this one. So with respect to Q hat, we can have this derivative, and setting it to 0, we can obtain optimal Q hat. So in here, omega Wi can be set. Wi, this is the weight, and this weight can be different for the sigma 1 and sigma 2, because sigma 1 is more uncertain than sigma 2. We can actually have more weight on sigma 1, more weight on sigma 2 and less weight on sigma 1, because it has larger uncertainty compared to sigma 2. So like this way. Omega 1 is equal to 1 over sigma 1 squared. If sigma 1 is large, then omega 1 will be small, vice versa. So we can utilize this weighting mechanism. Then if you solve this equation, then we get this final equation for Q hat. Q hat is actually the weighted average of Q1 and Q2. And their weight is actually proportional to the sigmas. So denominator is the total sigmas, and numerator is actually inversely proportional. So if you have Q1, then that should be sigma 2 squared. If you have Q2, then that should be sigma 1 squared in the numerator. Do you understand? Because if sigma 1 is larger, then that means we should focus on sigma Q2 rather than Q1. If you have larger sigma 2, then we should concentrate on Q1 rather than Q2. So that's why we have these equations. And then if you rearrange this one, then we get this equation, Q1 plus some factor and Q2 minus Q1. So you can see that initially we had this odometric information Q1, and we have some new observation Q2, and this observation is more accurate than the previous estimate Q1. We can assume that. Then their difference multiplied with this some factor should be added to the previous estimation, that we get the optimal estimate Q hat. Yeah, this is the Kalman filter actually. Kalman filter does this kind of thing. Yeah. This was the previous estimate Q1, and we have the new measurement Q2. Then their difference multiplied with some gain, or the factor, should be added to the previous one. Then we get the next optimal estimate. So this is actually very similar to the previous one. Yeah? We have the odometric information at x2, and we now have the new measurement like x2 2 prime using d. Then fusing them together, we get this one. Yeah. Smaller sigma and more sharp distribution should be obtained. Using the Kalman filter, you can do that. So in the Kalman filter notation, you can summarize like this way. This is called the innovation term, difference between the current estimate and the actual estimate, actual measurement. We have this innovation term, and multiply with Kalman gain. If you just add this term, then the previous estimation will be improved, like this way. So this is the Kalman filter mechanism. So in general, we can formulate the Kalman filter like this way. Yeah, given the linear dynamical system, xk plus 1 is fxk plus g uk plus vk, and y is the measurement equation hx plus w. So these are the linearized equations actually. So we want to solve xk, yeah, n-dimensional state vector. So in the mobile robot, it is x, y, and theta. X, y, theta. Unknown. We should solve this one. And u is the input vector. This is known from the encoder information. And y is the output. So it is the measurement. So we know this one. And we already know the system equation F and measurement equation H. We already know about that. We assume that. And V and W, they are white, German, Gaussian noise. And with the covariance matrix Q and R. We assume that we already know about this information. And Kalman filter is the recursion that provides the best estimate of this state vector X. So how does it work? It's very, very simple. Yeah? Very, very simple. So these system equation and measurement equations are given, and we first predict based on the rest estimate. Rest estimate means x hat k bar k. This was given, and using f, g, u, they are already known in advance, and h is already known. So we calculate like this way. So this is the prior information we can get. X hat k plus 1 by k, we have the prior information, and using this prior information, we can actually estimate the measurement also. And calculate correction based on prediction and current measurement. So this is the current measurement, actual measurement, and this is the predicted measurement. So their difference will be used to calculate delta x. So delta x term will be updated like this way. Delta x will be used to update the prior information to the posterior information. So we have 3 steps. The first one, prediction. Second, observation. Third, update. Yeah. Prediction, observation, update. We undergo those 3 steps in the Kalman filter. So in the Kalman filter, we usually have the initial information like x hat 0 by 0. In the slab, we assume that this is 0, 0, 0. Yeah. X, y is 0, and theta is also 0. We assume that. And we start from the 0, 0, 0. And P 0 by 0, this is the initial covariance matrix. We can put anything here. Yeah. So moderate value will be given here. They are given. And also F, H, system matrix, measurement matrix, they are given. And Q, R, they are also given. This is the system error covariance. This is the measurement error covariance. We are already given that. So we input this one here. Then we can propagate this equation. And also P0 by 0 is given. So we can also propagate this equation. So control input is also given. So we can propagate. And then we have the observation step. In the observation, we have the actual measurement y and the predicted measurement y hat. Y hat is given from here. So their difference is called the innovation. Usually denoted as mu, and this is called innovation. And each covariance is also calculated like this. S is the innovation covariance. So H, P, H transpose plus R. This was already given, and already given. So we can also calculate this innovation covariance. And also final stage is the update step. In the update step, we calculate the gain called Kalman gain. So this Kalman gain will be calculated like here. So H is given and P k plus 1 by k is already given from the previous prediction equation, and S inverse is already calculated from the observation step. Innovation covariance will be inputted here. And be sure that you have the inverse term here. So we have the matrix inverse operation in here. matrix inverse. So that means if you have some large matrix, large n by n matrix, then it will take some time in here. It will take some time. If it is 3 by 3, then it's very easy to calculate. You have some kind of lookup table to calculate. But if you don't have that, like 10 by 10 matrix, then it is not easy to calculate. Yeah? We should have some specific algorithm to calculate 10 by 10 inverse. Yeah? Like sure complement, you can utilize some mathematical tools to calculate this matrix inverse for larger matrices. So once you calculate this common gain, then you just multiply this one to the innovation term to get delta x. This is the delta x term. So just adding this delta x to the previous a priori information, then you get the posterior information. Also, p should be updated. This prediction error was propagated and error gets larger in this step, but in this step you can see that error will get smaller. Because we have the negative term here. S is always positive, and K transpose will multiply in front and rear, so this is also positive term. So we always decrease this P. So P will be getting smaller in this step. So P will be getting larger in this prediction step, but in the updated step, P will be getting smaller. So this process will be iterative over time. So this three process will be iterative. Okay, this will be iterative. And also, if you have the nonlinear equation like in the previous slide, so we already have that. This is the nonlinear equation, not the linear equation. So nonlinear equation. In that case, we have to linearize this one. Yeah, linearize. So we usually use the Jacobians to linearize this one. So Jacobians are used. So F was the system matrix, and system matrix is nonlinear now. So we use the Jacobian, and also measurement equation is also nonlinear. So we utilize the Jacobian of this one. So we calculate the Jacobian at first, and the other things are the same. So we are given F, H, and their Jacobians are already calculated, so we can utilize that. And the other things are actually the same. So this process is called the extended current filter. You linearize the original nonlinear equation, and the last step are the same as the original current filter. So this is the extended version, because we have linearized the original equation and utilized the Jacobians. So we call it the extended current filter, or in short, EKF. EKF. So until now, we have discussed how to utilize the map and localize the vehicle. But we can also build a map autonomously. Starting from the initial point, the robot should be able to autonomously explore the environment with its onboard sensors, get knowledge about, interpret the scene, build a map, and localize itself relative to this map. This is called the SLAM, simultaneous localization and mapping problem. So until now, we have discussed this part. From the encoded information, we predict the position and also predict the measurement. And given the observation, actual observation, we match them. And this innovation term will be used to update the current estimation. So we iterate this term. So in this case, we have assumed that we have already known map information. But in case if we have the unexpected observation, the map is not given, then you get unexpected observation. So in that case, we can add new features and extend the map. So you incrementally build the map. And also, if this unexpected observation is usually, then this information will be removed in the map information. So you can incrementally update, and some features will be added and some features will be removed from the map.